Okay, in this lecture we're going to do some motivation for this chapter on static beam differential equations and a little bit of revision of calculus as well to get us along. Okay, so here's a screenshot of some analysis of a beam. We've got a simply supported beam here with a UDL of 10 kilonewtons per meter for it looks like 6 meters, and then a point load of 20 kilonewtons here at 9 meters. And the analysis that they do is probably something that is familiar to you from maybe a different structural engineering module. And they kind of produce these graphs. But what we're going to do is we're actually going to find formulas for these graphs. So we're going to have as an input, well, there'll be a number of factors: the length of the beam, the type, is it simply supported, fixed ends, or cantilevered, what type of loads are on it, and we'll end up with formulas for the shear force at any point. So it'll be V of x. So say you want to find the shear force at 7 meters, you plug in x equals 7 into the formula for V of x. And it'll also be for the bending moment, the slope, and the deflection. Okay. So this approach, what you've done so far, is largely more of a qualitative understanding. Like for you to find out what's going on in x equal 1 is a little bit difficult at the moment. So in this chapter we'll learn how to find formulas for these, as we said. We'll learn the theory of how to do this for a great many types of loads, not just UDLs, point loads and linear loads, in theory a little bit more. And in the final section, which really belongs to the final chapter and might be examined in the fourth assessment, if there's a fourth assessment, we learn how to generate approximations when the methods of this chapter fails. Okay, so that's your basic motivation. Right, we just need a little bit of calculus review here. Now, the calculus in this is not that difficult, in my opinion. Really what you need to do in this thing is just practice a lot. And you also want to think of a kind of a skills-based approach to this. Now, what I mean by this is you're going to have your assessment, but if you know that you're not going into level 8, or you know, if you know you're finishing this year and you just want to do the assessment, that's okay. But actually that's not, no, I take that back. You're going to have a structural analysis module in the second semester, and you're going to want to be very, very good at this to be able to do that. Like, my understanding is that this is one small chapter in this module that represents even less than a chapter in the next thing, but I think a lot of the ideas in this chapter are built upon in the next thing. So you want to think of this as a skill that you're going to want to develop over the few weeks that you work on this, so that this stuff is actually that you don't just focus on the assessment for this module, that you get good at kind of all the questions in here. Good. Okay, so at the moment all we need to know about differentiation is the following. So so a polynomial is a function of this form that's sums of powers of x. For example, a parabola is a polynomial. An example of a polynomial is this thing, sums of powers of x. The degree of the polynomial is the highest power. So here the degree of f is 5. And in general, a degree 5 polynomial has 5 roots. There's 5 values of x that solve this equal to 0. Some of them can be complex numbers, some of them can be repeated. In other words, like for example with x squared plus 2x plus 1 equals 0, you get, that's degree 2 because it's x squared, but the 2 roots are both minus 1, they're repeated. In general, okay, we said this. For example, the example of, okay, we said this. Okay, however, if all roots are real and distinct, then the polynomial cuts the x-axis n times. So if you plot it, you can have complex roots which won't show up on a graph. We don't need to get into that. And if they're not repeated, for example, this one, 5 roots, it looks something like this. 1, 2, 3, 4, 5. And off it goes. And you'll see that it'll have, if you look at the derivative, it'll reduce the power by 1. And at degree 4, so this will be equal to 0 4 times. And of course, what happens when the derivative is equal to 0? You have a max or a min in general. 1, 2, 3, 4, 1 less. So potentially, again, you've got problems with complex roots and repeated roots, but in general, this will have 5 zeros and will have 4 turning points. And say if it was degree 8, it would have, in general, 8 zeros, 8 times cutting the x-axis and 7 turning points, except for problems with, as I said, complex roots and that. As an example, quadratics are degree 2 and have 1 turning point. So for example, this is like a plus x squared, and maybe if it's plus x squared minus 1, for example, it will have 2 roots, plus or minus 1, and when you differentiate it, you get 2x, and that is equal to 0 to 0, you get 1 turning point. Okay, so we differentiate these using the sum, scalar, and power rules. The sum just means if you've got a sum, you differentiate term by term, and the scalar rule says if you have a constant, you should fix the constant and then differentiate. That'll be something I'll be recommending. It's not something that you've typically been doing. Typically, you've been doing something like this. Say 2x to the 7, you would multiply the 2 by the 7. Now for various reasons, it works fine here. It's 14x to the 6. But I'll be recommending this approach where instead you fix the constant 2, then differentiate x to the 7. Now if you get things right, it's no problem. But as we'll see down the track, and also for next semester, if you're picking the elective maths, you're better off to do this thing. Now if you use the sum and the scalar rules, this is what's called using linearity, differentiating term by term, fixing constants. So you'll hear me say this quite a lot, term by term, fixing constants. And obviously the power rule is just saying how to differentiate x to the 7, but I assume that's no issue for us. So this is an example of a cubic, ax cubed. Notice that it has 3 roots, 3 real roots, and 2 turning points, because the derivative of an ax cubed is like a 3ax squared, which is a quadratic, which is equal to 0 once, twice. So you see in general a cubic will have 2 turning points, max and a min. In some sense this is typical. So next thing is, if you have a function, you know how to find its derivative, so that's kind of easy. Now consider the inverse problem. If you have the derivative of something, how do you anti-differentiate it? And this is somehow more difficult. So there's different kind of notations I could use here. So this thing we would call d dx. You differentiate a function, you get the derivative. The antiderivative, you never see anything like this, but it wouldn't be the worst way in the world to do it, is to write it as d dx inverse. So now we won't really see this for various different reasons, but this would be called anti-differentiation, and that's what I'm going to call it. Now you probably know it more as the inverse of differentiating is integrating. But personally, I've an issue with that. I think it causes some confusion. Now, while I appreciate this is a integral sign, if there's no limits, it means anti-differentiating. In my opinion, the word integral should be kept for when there's limits. So to calculate an integral, just to show you what I'm talking about, we would have done this, I think, in a previous lecture. So say if you're anti-differentiating between 0 and 1, x squared dx. This is an integral, but to do an integral, you anti-differentiate the x squared, and we'll see it written down soon now. The antiderivative of x squared is x cubed over 3. And then you do top limit minus bottom limit. So it would be 1 cubed over 3 minus 0 cubed over 3. I hope this isn't confusing things, but to me, like what this thing is anti-differentiating. This isn't anti-differentiating, because you're putting in x squared 0 and 1, you're getting out a number. Like, you don't differentiate to get a third to get this. The anti-differentiation is just here, where you go, the derivative of x cubed over 3 is x squared. The antiderivative of x squared is x cubed over 3. You do an anti-differentiation to calculate an integral. And mostly in this chapter, and actually this module, there was an integral in an earlier lecture. I think it's the only one I've ever had in this module. Now, you'll see one here and there in theory sections, but you don't actually have to do them. Okay, so this is what we're talking about. We need to be able to anti-differentiate. So here, given a function cos of x, find an antiderivative of this. So find something that differentiates to give cos of x. And you can have a think, you can look in your tables, whatever. Antiderivatives include sine of x, but there's more. If you differentiate sine of x, you get cos of x. But if you differentiate sine of x plus 2, you also get cos x. And if you differentiate sine of x minus pi to the power of 10, this is just a constant, pi to the power 10. So the derivative of a constant being 0, if you differentiate term by term, the derivative of sine of x is cos of x. So this is typical. You find one particular antiderivative of sine of x, then all of the antiderivatives are given by that plus a constant. Now you can get a bit technical. C can be a little fancier than a constant. It just has to be piecewise constant. Like it could be equal to 1 for positive x and minus 1 for negative x, but we don't really need that. Okay, so here suppose that f of x equal to x to the 5, find all antiderivatives. Now we could just go to the tables here, but we don't have to do that necessarily. Let's kind of just figure it out. So think about what would you have to differentiate to get x to the 5. Well, to end up with an x to the 5, because remember when you differentiate you lower the power, it'll have to have been higher. So think about x to the 6. So when the thing that differentiates to give x to the 5 is going to be like x to the 6. Now let's differentiate x to the 6. You get 6x to the 5. So this is 6 times too big. So if you divide it by 6, then it'll work because anti-differentiation is linear. And this is the familiar thing you've seen before. To anti-differentiate a power of x, add 1 to the power, divide by the new power, and we do plus c. Now if you get some extra information, this can pin down, there's loads of antiderivatives, but if you get some information about either f of x or this, you might be able to find what the c is and narrow it down to one function. Now the information for us will consist of knowledge about the beam. Is it a simply supported beam? Is it fixed ends? Is it cantilevered? The constants we're going to come up with are going to be, the extra bit of information will be given by that. And in fact, we're going to have 4 constants and they're all going to have kind of physical meaning. So like one of them is going to be the reaction at A, at the left side of the beam. One of them is going to be MA, the bending moment at the left side of the beam. One of them is going to be called C1 and it's related to the slope at the left support. And the other one is C2, which is going to be related to the deflection at the left support. And if it is a left support, if it is supported, that's going to be 0. Indeed, that's always going to be the case. Okay, so let's look here at an extra bit of information and how that affects what we're doing. So a curve satisfies, so you got some function, some curve, and the derivative of the curve, or the slope of the tangent, whatever way you want to think about it, is equal to 3x squared, and the curve passes through this particular point. Now I might just kind of draw a picture here, give you an idea of what's going on here. So I'm going to draw some curves that all have a dy dx equal to 3x squared. So what do you differentiate to get 3x squared? The answer is x cubed. Now x cubed looks something like this. Okay. Now if I shift this graph up, or if I shift it down, what you notice is as you look along a single value of x, particularly if I did this properly, all these curves are supposed to be parallel. Now I know I haven't done it properly, but I'm supposed to. They're all bad. They're all parallel. So this is a manifestation of the fact that, like there's loads of I can shift these up like little point ones. There's infinitely many solutions. This is a manifestation of this. Each value of c gives you a different solution. So for example here, the one that goes through the origin, this corresponds to c equal to 0. This one might correspond to c equal to -1. This one might correspond to c equal to 1. So there's loads of different solutions. Now we're looking for the solution that goes through the points, say x equal to 2, y equal to 5. And so we need to find the value of c so that the curve goes through that point. So I might draw it look something like this. Actually, well, I know it should have been down there, but anyway. So if you have that extra piece of information, which for you might be something like, oh, the curve is simply supported, so the bending moment at 0 is 0, then you can narrow down the value of c. Okay, so we have a particular antiderivative. This is x cubed, hence all functions of the form x cubed plus c are antiderivatives. So we know that y of x has to be of the form x cubed plus a constant. Now what we have to do now is use our boundary condition, our initial condition, our bit of information to find out what c is. Now there's a bit written down here. It says, recall that we write this is the x coordinate and this is the y coordinate. So what this means is that when x is equal to 2, y is equal to 5. So what we can do is we can sub in x equal to 2 into this. So the value of y at 2 is equal to 2 cubed plus c. So the y value at 2 is equal to 2 cubed plus c, and we know that this has to equal 5. And so we have a little tiny equation in c. We've got a plus 8 here that we don't want. What's the inverse of plus 8? Take away 8. Take away 8 from both sides, you end up with c is equal to -3. So the equation of the curve is y of x, if we're thinking in terms of a function, y is equal to x cubed minus 3. Okay, so we've got a proposition here. This is just, all this is actually saying is that antidifferentiation is the word linear. You're going to hear linear a lot in this module, and also if you pick the elective next semester. But it basically means that if you are antidifferentiating a sum or a difference, because that's also a thing, you can do it term by term. Antidifferentiate term by term, and you can also fix constants. So we're going to do that. And also something that you should know is antidifferentiating powers. Add 1 to the power, divide by the new power. Okay, so let's go. So we're going to do this antidifferentiate term by term. And these two symbols together mean antidifferentiate with respect to x. We're going to do term by term, fixing constants. So first we have x to the 4, and the antiderivative of x to the 4 is add 1 to the power, divide by the new power. Now we're going to fix the constant 4. And then, now the only constant that you can fix is when it's multiplying a function. If a constant is on its own, well, we'll come to that in the next example. But if it's multiplying something, you can fix it. So fix the 4, antiderivative x cubed. Well, here we see add 1 to the power, divide by the new power. Now we want to do a plus c, but maybe just before I do that, I might tidy this up a little bit, because 4 divided by 4 is 1. 1 by x to the 4 is x to the 4. So I get x to the 5 divided by 5 plus x to the 4. And I want a plus c here as well. Done. Okay. And the next question. So again, term by term, fixing constants. Now the 4 here, or the -4, is like a -4 multiplying. You can fix that as well if you want. So the antiderivative of x squared is x cubed over 3. Then fix them. Now if it was just minus x, you can fix the minus. So the term by term works with plus or minus. Fix the -4. Now what's going on with x? What is the antiderivative of x? Now probably the easiest way to do it is write x, recognize x as x to the 1. And so the antiderivative of x to the 1 is add 1 to the power, divide by the new power. The 2 is a little bit special. You have to think, what do I differentiate to end up with 2? Have a little think for yourself. What do I differentiate to end up with 2 would be 2x. And then again, before we put in our constant, maybe we tidy it up. Although actually in the questions that we'll be doing, you won't be doing that. So maybe I'll just put in the plus c now. So term by term, fixing constants. Okay, so here what we have is just the theorem that we mentioned and the picture we drew before. So if you have some antiderivative, then every antiderivative has this form for some constant, and this is geometrically obvious. You could like actually take this curve going from here and shift it upwards, so it becomes discontinuous. I'll show you what I mean here, but this is really complicating things, but you could do it. So then just have what's called a discontinuity and then continue on your way. So this red curve actually, the constant changes. It's called piecewise constant to see, but anyway, that's really complicated things, I'm afraid. So the idea though is shifting a graph up or down does not change its slope. So if I draw this vertical line here, so this is a particular value of x, and if I look at the slope at this point, which means the slope of the tangent, all these curves should be parallel. And indeed they are. Okay, so that's why adding a constant just doesn't change the slope. And remember, the antiderivative is asking for the curve with a particular slope, and there's loads of answers. So this is this notation we said. Okay, that's your mathematical background for the maths in the beam equations.